Hi everyone, and welcome to this video that accompanies section 22.3 of the book Algorithms Illuminated Part 4. This is a section about the big picture of what chapter 22 is going to look like. So as we've mentioned, there's going to be 19 problems that we're discussing, all NP-hard, all proved NP-hard via reductions from the 3-sat problem. So there's 19 problems and 18 reductions to keep track of. Let's get organized. First, a quick sanity check. As algorithm designers, we're accustomed to designing reductions for the honorable purpose of spreading computational tractability. Whereas at NP-hardness, we're using reductions to spread computational intractability, which goes in the opposite direction. And it's really easy to mix up those directions. So let's have a quiz to sort of hone our understanding. If you watch the video about mixed integer programming or MIP solvers, we show that the knapsack problem is easily formulated as a MIP. So in other words, the knapsack problem reduces to the mixed integer programming problem. So what does that then imply? Okay, so the correct answer is correct answers are the second and third ones, B and C. The easiest way to see why is just to remember the cartoon we had about a problem A reducing to problem B and the directions that tractability and intractability spread. Suppose a problem A reduces to a problem B. If we're talking about spreading tractability, then remember that goes in the opposite direction of the reduction. So if problem A reduces to B, then tractability of B implies tractability for A, right? Given a polynomial time algorithm for problem B, you would just compose that with your reduction from A to B to get yourself a polynomial time algorithm for A, showing that A is tractable. Whereas intractability spreads in the opposite direction of tractability, that is in the same direction of the reduction. Remember the two-step recipe for proving a problem B is NP-hard is you take an NP-hard problem A and then reduce A to B, and that spreads the intractability from A to B. So for us in this quiz, right, we have the knapsack problem reducing to the MIP problem. So the knapsack problem is our problem A, the MIP problem is our problem B. So computational intractability goes in the same direction from knapsack to MIP, and that is exactly what answer B says. Whereas answer A has the spread of intractability in the wrong direction. Okay, so B is correct because the intractability will spread from knapsack from the problem A to the problem B, MIP. And then for the same reason, answer C is also correct, okay, because computational tractability spreads in the opposite direction. So given a reasonably good algorithm for MIP, you get a reasonably good algorithm for knapsack just by composing the reduction from knapsack to MIP with the assumed reasonably good algorithm for solving MIPs. With that sanity check on your understanding out of the way, we can proceed to talking about the 18 reductions by which we will generate 18 new NP-hard problems, in addition to the 3-sat problem. In this cartoon, we're going to have 19 blobs corresponding to 19 computational problems, including all of the ones that we've discussed thus far in this video playlist. We're going to have an arrow from one problem to the other if there's a reduction in that same direction. So an arrow from a problem A to a problem B if A reduces to B. And intractability is going to spread in that exact same direction. So the mother of all NP-hard problems, the Cook-Levin theorem, we're going to start from 3-sat. Now we're going to have a tree directed outward from 3-sat. So the NP-hardness will spread from 3-sat through this directed out tree to the other 18 problems. Let me now just go ahead and draw the rest of this directed out tree. Then we'll discuss which of these reductions we've already seen or are easy, and then which reductions are going to be the hard ones occupying the next 4 videos. That's a bit overwhelming, probably. It's a lot of problems. You will notice almost all of these problems we have discussed in the past. I'll tell you about the other ones in a second. It's also a lot of reductions, 18 reductions, but actually some of those we've seen in the past also, as we'll discuss. Let's start with the one truly trivial reduction. You'll see there's an arrow from the 3-sat problem to the sat problem, saying the 3-sat reduces to sat. And that's completely trivial, right? Because 3-sat is literally a special case of sat. It's the special case of the instances where each constraint happens to be a disjunction of at most 3 literals. So certainly any subroutine for sat automatically solves 3-sat. One of these reductions, while not trivial, is something we've actually already seen. We saw it back in the opening sequence of videos corresponding to chapter 19. And that's the reduction from the directed Hamiltonian path problem to the cycle-free shortest paths problem, when you can have edges with negative lengths. So back then, we were talking about using reductions to spread intractability. We introduced the 2-step recipe, and I just wanted to give you a quick glimpse of what that 2-step recipe looks like in action. And the particular case study we used way back in chapter 19 is we took on faith that the directed Hamiltonian path problem is NP-hard, something we'll prove in this chapter, and then we showed that that problem reduces reasonably easily to the problem of computing cycle-free shortest paths. And the reason that was interesting is it sort of explained the limitations that we had on the shortest path algorithms that we were discussing in an earlier book of this series. So like the Bellman-Ford algorithm and the Floyd-Warshall algorithm, they're guaranteed to compute correct shortest path distances only in the special case of graphs that have no negative cycle. And then finally, from this reduction from directed Hamiltonian path, we finally understood why. Because if the Bellman-Ford or Floyd-Warshall algorithms were correct more generally, even when graphs did have negative cycles, that would actually refute the P not equal to NP conjecture. So that leaves us with 16 of the 18 reductions to understand. Now, of those 16, 11 of them are actually quite easy, and all show up in the book as end of the chapter exercises. So let me just enumerate those 11 relatively easy reductions now, and I'll give you some hints along the way of what those reductions actually look like. For example, one pretty easy one is the reduction from the independent set problem to the clique problem. So let me remind you what these two problems are. They're both problems about undirected graphs. So an independent set of a graph, that's a subset of vertices that are all non-adjacent. So there's no edge that has both endpoints in that subset. And a clique is exactly the opposite. Okay, so that's a subset of mutually adjacent vertices. Every edge with both endpoints in that set is in fact present in the graph. In the independent set problem, we're looking for the maximum size of an independent set. In the maximum clique problem, we're looking for a clique of maximum possible size. If someone hands you a efficient subroutine for the clique problem on a silver platter, it's very easy to extract from that an efficient algorithm for the independent set problem. If I give you an instance of independent set, I say, find me the biggest independent set you can find. What do? You toggle which edges are in and which edges are out of the graph. Okay, so you take the complement edge set of the graph that I gave you, that turns all the independent sets into cliques. Now you run the assumed subroutine for computing a maximum size clique. It hands it back to you, and now you just toggle those edges back, and you get a maximum size independent set of the graph that you started with. Something very similar is going on in the reduction from the independent set problem to the vertex cover problem. So what's the vertex cover problem? So now you want to find a vertex cover, which means you want to find a subset of vertices that includes at least one endpoint of each edge. So you want it to be the case that there's no edge, both of whose endpoints are omitted from your subset. And then, of course, all the vertices would be a vertex cover. That would cover both endpoints of all the edges. So you want a minimum size vertex cover. Okay, the smallest subset of vertices such that every edge has at least one endpoint covered. And so here the trick is to realize that in any graph, if you take any independent set, the complement of the independent set is a vertex cover, okay, and vice versa. So this means that if you want to find the maximum size independent set of a graph, and I give you a subroutine for computing the minimum size vertex cover, all you need to do is invoke the subroutine for finding the smallest vertex cover. You take the complement, so you take all the vertices that are not in the smallest vertex cover, and that's going to be a largest possible independent set. Let's go ahead and follow the rest of the arrows down that directed path. Okay, so next we have that the vertex cover problem reduces to the set cover problem. What's the set cover problem? Well, the input looks a lot like it did in the maximum coverage problem. So there's a ground set of elements. I give you a collection of subsets of that ground set. But rather than having a budget on how many subsets you can pick, I give you the requirement that your subsets have to cover everything, have to cover the whole ground set, and then your job is to cover the whole ground set with as few of the subsets as possible. That's the set cover problem. Turns out the vertex cover problem is simply a special case of the set cover problem. So given an efficient subroutine for set cover, it immediately gives you an efficient subroutine for vertex cover. Why is vertex cover a special case of set cover? Well, just think of the ground set as being the edges of the graph, and you're going to have one subset for each vertex of the graph. And the elements of that subset are going to be the edges incident to that vertex. So in effect, it's almost like subsets correspond to stars in the graph that you're given. And if you think about it a little bit, you'll realize that set covers of that set system are exactly correspond to the vertex covers of the original graph. Next, the set cover problem reduces to the maximum coverage problems. Remember, these two problems have almost the same input. The difference is that in maximum coverage, I give you a budget on how many subsets you can pick, and you want to cover as much stuff as possible. In set cover, I give you a requirement that you have to cover everything, and you want to pick as few sets as possible. So, if you were given a subroutine for the maximum coverage problem, how would you use it to solve the set cover problem? Well, you'd take your maximum coverage subroutine, and you would ask it, for the maximum amount that can be covered with one set. Then you'd ask it again for the maximum amount that could be covered by two sets, and then again by three sets, and so on. And it would be handing you back the maximum coverage that could be achieved with that number of subsets. At some point, once your budget K is high enough, then the maximum coverage subroutine will actually be able to cover everything. And so the first value of K, like if K equals 17, was the very first time that the maximum coverage algorithm was able to cover the entire ground set, then you know that that's the answer for your set cover problem. Those 17 subsets are a minimum size set cover in the set cover instance that you started with. Finally, along this path, and this is something we mentioned back when we were discussing influence maximization, is that the maximum coverage problem is basically a special case of influence maximization. That's why it was so cool we were getting just as good an approximate correctness guarantee for the more general problem, that 1 minus quantity 1 minus 1 over k raised to the k. Let me give you kind of a quick hint of how to view maximum coverage problem as a special case of influence maximization. I'll leave it to you to think through the details. So suppose we're given an instance of maximum coverage, right? So we have our ground set and we have our subsets. We need to somehow view this as an instance of influence maximization. So in particular, we somehow need a graph. So what we're going to do is we're going to have two rows of vertices. In the top row, we'll have one vertex for each of the subsets that we were given in the maximum coverage instance. In the bottom row, we're going to have one vertex for each of the elements of the ground set that we were given in this maximum coverage instance. Those are going to be the vertices. For the edges, you're going to have a directed edge from each vertex corresponding to a subset to each of the vertices corresponding to the elements that it contains. That's going to be the graph. The last thing the influence maximization subroutine is going to be expecting is an activation probability. We're just going to set that equal to 1. Think this through, and what you'll find is that the influence maximizing subsets in this graph, they're going to be subsets of k vertices in the top row that activate as many vertices in the bottom row as possible, and that's going to correspond exactly to the coverage of those corresponding k subsets. Moving on to a different part of the graph, let me just talk briefly about the traveling salesman problem. Let's not worry right now about why the traveling salesman problem is NP-hard. Let's worry about the two edges going out of the TSP, so the reductions from TSP to two other problems. So let's start with the traveling salesman path problem. So this is just the slight variant of the TSP, where instead of a tour that loops back on itself, you want a path, but still a path that's cycle-free and visiting every vertex. So this is going to be a path where if there's n vertices, there'll be exactly n minus 1 edges, visiting each of the vertices exactly once. And in the path problem, you want a minimum cost such path. A reduction from the TSP to this traveling salesman path problem is then just a way of using an efficient subroutine for computing the best path and extracting from that subroutine the best tour in the original instance. And this is not hard to do. I'll leave it to you to think through the details. But basically, it's possible to do a little bit of minor surgery on the TSP instance that you start with, so that if you feed this sort of slightly modified version of the graph to a subroutine for computing a traveling salesman path, you're actually going to trick that subroutine into computing for you a tour in the original graph that you started with. Again, I'll leave that as an exercise for you to think through. The exact same idea works for the minimum cost k-path problem that we discussed at length. Okay, so the problem of given a graph with edge costs, compute the k-path, so a path with k minus 1 edges, k distinct vertices, no cycles, the minimum cost k-path. Exact same idea. We'll prove that that problem is NP-hard as well. Next, let's talk about the Hamiltonian path problem. So because some of the graph problems we care about are most naturally directed graphs, like cycle-free shortest paths, whereas for others, we're focusing on undirected graphs, like in the TSP. it's useful to have two versions of the Hamiltonian path problem. One for directed graphs, again, where you're looking for a simple path that visits every single vertex exactly once, or the same version, the same problem in undirected graphs. And as you'd hope, these two problems are almost the same. There are very easy reductions in both directions. So for example, if you start from an undirected graph, and I give you a subroutine for the directed case, you can transform your undirected graph into a directed one just by replacing each undirected edge with a directed edge going in either direction. If you think about it, if you compute a directed Hamiltonian path after you've bidirected all the edges, it's easy to extract from that an undirected Hamiltonian path from the graph that you started with. On the other hand, if you start from a directed Hamiltonian path instance, so a directed graph, there is a way, it's a little more complicated, but not much. There's a way to turn a directed graph into an undirected graph so that after you compute an undirected Hamiltonian path in the undirected graph that you've produced, you can extract from it a directed Hamiltonian path in the graph that you started. Okay, so the upshot is, again, just using a very minor surgery on the graph, there are reductions either direction between the undirected or directed Hamiltonian path problems. Let's now zip over to the far left of the slide and talk about the two problems that we discussed semi-reliable solvers for, the SAT problem and mixed integer programs. So when you have a sort of feasibility problem, like graph coloring or whatever, usually SAT is the most natural encoding of it. But whenever you have an encoding using satisfiability, if you wanted, you could have an encoding using mixed integer programming as well. Now, mixed integer programming is about optimization, so you would expect there to be an objective function. But if all you're trying to do is encode an instance of SAT, you don't need an objective function. You just have sort of a placeholder objective function like maximize 0. Then all you need to do is translate the logical constraints in the given SAT instance, so a disjunction of literals, into arithmetic constraints, into inequalities. And as you'd probably expect in your integer program, you're going to have one 0, 1 decision variable for each Boolean variable in the SAT instance, where the value 1 corresponds to true and the value 0 corresponds to false. And then if you think about it, each of the disjunctions of literals is quite easily translated into an inequality. Saying something like, x1 plus x2 plus x3 is at least equal to some constant. There's other ways you could also argue that mixed integer programming is NP-hard. So for example, as we saw, it includes knapsack as a special case, and eventually we'll be proving that knapsack is NP-hard. It's very easy to encode the independent set problem as a mixed integer program, etc. But I chose one particular proof of NP-hardness in mixed integer programming, here going via the satisfiability problem. The last of the easy reductions concern a problem we haven't discussed yet, the subset-sum problem. So in the subset-sum problem, I give you n positive integers, so 17,234, 19 million, blah, 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 blah. I give you n positive integers. And I also give you a target, 21,325,173. And the question is there a subset of the n numbers whose sum is exactly equal to that target? Yes or no? Okay, so it's not an optimization problem, it's just feasibility. Is there not a subset with exactly the target sum? We will be proving that the subset sum problem is NP-hard, but here I just want to record the fact that if subset sum is NP-hard, it will immediately imply NP-hardness of two problems we have discussed at length, the knapsack problem and make-span minimization. It turns out subset sum is basically a special case of both of these two problems. So if subset sum is NP-hard, certainly so are the more general problems, which we actually care quite a bit about. Subset sum is basically the special case of knapsack, where the item sizes are the same as the item values, and it roughly corresponds to the subset of make-span minimization when you have only two machines. So those are the 11 kind of easy exercise reductions that I wanted to mention. So that leaves us with 5 reductions. 4 of those we will be covering in the next 4 videos. The 5th one, even though it's not that easy, I'm still going to leave it as an exercise, and that is the proof that the graph coloring problem is NP-hard. The difficulty of that reduction is, roughly on par with the reductions that we're going to see in the forthcoming videos. I could have had another video with this reduction, but by the time we finish these 4 reductions, you're going to be sick of them. So you're going to be glad that I just sort of deferred this as an exercise for those of you interested to do in the privacy of your own homes. That leaves us with 4 harder reductions. So we're going to start in the next video by reducing the 3-sat problem to the independent set problem. Once we have that reduction from 3-sat to independent set, at least assuming the Cook-Levin theorem, assuming 3-sat is NP-hard, At that point, the hardness will flow all the way to the end of that path, including to the maximum coverage and influence maximization problems. The next order of business will be to establish that the traveling salesman problem is NP-hard. That's really the canonical NP-hard problem, so I certainly want to show you why it is, in fact, NP-hard. So we have two steps to do there. The first one is going to be another reduction from 3-sat to a graph problem, this time not to independent set, but rather to the directed Hamiltonian path problem. So that'll be in the second of the forthcoming videos. That reduction will establish NP-hardness of the directed Hamiltonian path problem, again, assuming the Cook-Levin theorem. As we discussed, the directed and undirected Hamiltonian path problems are not that different. So once we know the directed version is NP-hard, we also know the undirected version is NP-hard. And then there's actually a pretty easy reduction from the undirected Hamiltonian path problem to the traveling salesman problem. So we'll do that in the third of the forthcoming videos. That'll be the easiest of the four, and that'll finally fulfill this promise that the traveling salesman problem is indeed an NP-hard problem. That leaves us with one last reduction, which will be in the fourth of the forthcoming videos, a reduction from the independent set problem, which again will be proving NP-hard in the next video, to this subset sum problem, which again, by virtue of it being a special case of the knapsack and make-span minimization problems, that will immediately establish that those two problems are NP-hard. And what's interesting here is that, knapsack and the subset sum special case, those are problems, they don't involve these complicated objects like graphs or something like that. The input to those problems is just a bunch of numbers, just n numbers. And in particular, we know we can solve the knapsack problem, and therefore the subset sum special case, in pseudo-polynomial time, using an algorithm that runs in time proportional to the magnitude of the input numbers. Now, that's not what we want. We really want to run in time polynomial in the input size and the number of digits needed to represent the input numbers. And this NP-hardness result is interesting because it explains why we can't get what we want. It explains why, for the knapsack problem, we're really stuck with this running time that depends on magnitudes of the input numbers rather than on the number of digits in those numbers. The next 4 videos will be filling in these gaps and presenting those proofs of those final 4 reductions. Before we do that, I kind of feel like I should level with you, because NP-hardness reductions, including some of the ones we're about to see, they can be kind of painfully messy. And to be honest, pretty much nobody remembers the details of any NP-hardness proofs. All that said, there's still some pretty good reasons for seeing a few of them. So let me just be explicit about what the goals are for going through these NP-hardness reductions over the next 4 videos. Goal number 1 is to fulfill a bunch of promises that I owe you from previous videos in this playlist from earlier in the book, right? So problem after problem that we tackled, I kept saying, oh, bummer, this is NP-hard. Oh man, this one's NP-hard too. We got to compromise on correctness or compromise on running time. We can't get what we want. And, I feel a little bit fraudulent if I didn't actually explain why those problems are NP-hard and why we needed all those compromises that we went through in the videos corresponding to chapters 20 and 21. So that's the first reason we're going to go through these reductions. The second goal is to give you some ammunition for carrying out the first step of the simple 2-step recipe for proving problems that are NP-hard. Right? Step 1 is you have to choose a known NP-hard problem. So going through these reductions, that'll really solidify sort of our knowledge of a bunch of NP-hard problems that you can then use in your own NP-hardness reductions. If 19 problems aren't enough for you, well, let me refer you to the classic book by Michael Gary and David Johnson, Computers and Intractability, A Guide to the Theory of NP Completeness. This book is all the way back in 1979, and don't forget, the Cook-Levin theorem's around 1971, and Karp demonstrated the power of NP-hardness around 1972. So this is just later that same decade. So it's still sort of early days, but already in 1979, there were hundreds of NP-hard problems known. And that book includes a compendium of over 300 NP-hard problems, which is a great place for brainstorming your own NP-hardness reductions. Indeed, it's very hard to think of any computer science books from 1979 that remain as useful as Gary and Johnson to this day. Finally, I don't expect you to really remember the details of any of these NP-hardness reductions, say a year from now, or frankly, even like a week from now. But still, this exercise should be empowering to you, right? So if at some point in the future, your boss hands you a problem and says, your raise for the year depends on whether you can prove that this is NP-hard by next week, you should feel like that is something you could do if you really needed to, right? They're messy, they're problem specific, but look, you're just about to watch a few 20-minute videos with examples of reductions. You're going to understand them. You're going to be like, yes, if I really had to do this, I could. That's enough about the big picture of chapter 22. Let's dive into the reductions, starting with the independent set problem. See you in the next video.